Okay, let me introduce the speaker of the seminar of this afternoon, Professor Alejandro Ibarra. Professor Alejandro Ibarra was born in 1974 in Spain. He obtained his PhD at Universidad Autónoma de Madrid in 2000. He has worked at Oxford University, some in Geneva, Institute for Theoretical Physics in Madrid, and DESI, Particle Research Center in Hamburg. In 2008, he became professor of theoretical elementary particle physics at Technical University of Munich. His scientific research focuses on theoretical elementary particle physics, in particular physics beyond the standard model, neutrino physics, supersymmetry, and astral particle physics. He has worked on models of neutrino masses, their electronic decay, the indirect detection of dark matter, and leptons genesis as a model for the origin of the universe method and the matter's asymmetry. Okay, let's welcome the speaker.
Thank you for this opportunity, for the introduction, and to all of you for coming here. So I don't have any slides, so please interrupt me at any time for questions, especially the students. So it's basic questions, advanced questions, doesn't matter, or curiosity questions, because I can hear more to discuss with you after the presentation. And yes, so what I'm going to talk about today is about this recent paper with Mark Hiska, who is a PhD student, and Jerome van de Castelle, who is a postdoc in Munich, and this is a model connecting the baryons to the dark matter of the universe. Okay, so this is something that perhaps you all know very well, that the standard of cosmology is well grounded physically and can explain with great accuracy a large number of cosmical data. So here you can see the anisotropies of the temperature of the cosmic microwave background radiation, and these are the polarization map also derived by the Planck collaboration. And here what you can see in the red points are the power spectrum or the temperature anisotropies. This is about the spectrum, the polarization, this is the close polarization and temperature anisotropies. And here the blue line corresponds to a model. So it is quite clear that the model can reproduce with a great accuracy all this huge amount of data. So what is this model? It's a model of cosmology. The standard of cosmology is based on the Einstein field equation. So in this respect, it is well grounded physically and theoretically. So here on the left-hand side, in the left-hand side, you have the Rich tensor, which is scalar, metric tensor. In the right-hand side, you have the energy momentum tensor. So again, with some well-motivated assumptions, one can write the line element or the metric tensor just in terms of two parameters, which are the scale factor and the curvature parameter. And now, perhaps more importantly for us, is this right-hand side of the equation, the energy momentum tensor, that generically in the context of cosmology is decomposed into three parts. The first part is the contribution to the energy momentum tensor from the radiation, which is this component of the cosmic fluid, where the pressure is equal to 1/3 of the energy density. The second one is the dust, that corresponds to a fluid that has no pressure. And then the last one, which is a fluid that has a pressure equal to minus the energy density, which is usually called the cosmic constant. So what is quite remarkable is that with these different few parameters, plus a couple more that I will not discuss, but just with 6 few parameters, it is possible to reproduce this big amount of data and many more just in terms of 6 parameters. So in particular, these 6 parameters tell us that the density of the radiation is about 10 to the power 4 spherical density. The spherical density is given by this number, 2 times 10 to the power 26 kilograms per cubic meter. Also, the dust amounts to 0.32 of this physical density, and also all these observations indicate that 15% of this dust is luminous and 85% of this dust is non-luminous. And finally, today, the cosmic constant is the dominant component of the density, which is 0.68 theoretical density. And then
The first peak around 500 is corresponding to the total energy density. Right? Total energy.
Yeah.
So it means the universe is especially flat.
exactly. So
And the
this,
second peak corresponding to the total matter.
yeah. Yeah, so it is also quite remarkable that if you take the sum of these different components, and you obtain a total density is equal to the critical density, that means that this curvature parameter must be either 0 or very, very close to 0, which is also another puzzle. So it has been a big success of cosmology in the last 30, 40 years to establish these different energy densities. But still we have many open questions. So one of the big open questions is why is the universe especially flat? So why the sum of all these densities corresponds to the critical density, especially knowing that it's an unstable point in the cosmic evolution. And for this there are some interesting ideas still not tested, which is the cosmic inflation. I will discuss this in my talk. Also something which is puzzling about this cosmic pi that has been derived by the Planck collaboration is why the density contributions from the luminous, this one, and the non-luminous dust are comparable. So another big question, or many others, is why the contributions from the matter component, which is about 30%, corresponds mostly, factor of 2-3 different, to the contribution to the total density comes from the cosmic constant. And this is even more puzzling because this is dust, so they evolve with the redshift in exactly the same way, so this ratio stays constant for the contribution, but this ratio between the cosmic constant and the dust changes with the redshift. So this one stays constant with the cosmic time, and this one increases with the redshift to the power of 3. Today, turns out that this component is comparable to this component. And then finally, and that is maybe what I'm going to discuss today, and also since most of us are particle physicists, is whether one could have a fundamental description of these three cosmic fields. Because the cosmologists, they are quite happy with this picture, so they have been able to determine all the parameters taken here in the Einstein field equations, the cosmic field equations. But as fundamental physicists, we would like to have a fundamental understanding of what is the radiation, what is the dust, and what is the cosmic constant. And in particular, whether these components can be described in terms of quantum, which is what will be important.
All those components are described by perfect fluid. So we need to connect it to the quantum field.
Yeah, exactly. That is one of the questions. I will not go that deep in my talk, but at least this is one of the questions that we still have in cosmology. And as you're saying, normally we assume that these different components are not interacting, but it would happen that the dust, luminous matter and non-luminous matter would interact. We discussed before, the luminous could interact with that matter, but it's not precluded by observations. Also, the cosmic constant could interact with that matter, and that is also not precluded by cosmic data. And then, if these interactions are turned on, then this picture could change. But gives you additional constraints on this picture. But in the simplest picture, it is quite remarkable that the simplest picture can reproduce so nicely the data. So, we are particle physicists, so we work with the standard of particle physics. So this model is also well grounded theoretically. It is based on quantum theory, it's based on the gauge theory, it's literally closer to class 1, and you have this funny matter content that is not totally understood, but it's just what nature has created. So you have here these 6 quarks, we have the trace leptons, neutrinos and neutrinos of the gauge interactions and the physics. So it is possible with this table of fundamental particles to explain these different components of the cosmic fluid. Well, for the radiation, yes, and this is something which is well established nowadays, that the standard model of particle physics can explain quite well the radiation content of the universe. So to explain this part, we need to have the photon, which is what is given by the standard model, which is known to be radiation, by definition almost, but in addition we have these neutrinos. So even if the neutrinos have not been studied by neutrino experiments from cosmology, we would have known that there are three relativistic particles in the universe, and precisely they correspond to the neutrinos. And both the cosmic macro radiation and the photosynthesis indicate that there are three neutrinos, reactive neutrinos, and not more or less than the reactive neutrinos. At least this part of the energy of the tensor is well understood in the context of the standard. So second part about the non-luminous matter. So here it is also well known by all of you probably that we have many particles in standard model, but none of them is at the same time non-luminous, cosmically stable, and produces a pressure exclude. So here you have non-luminous, you have to exclude all the particles that have electric charge or that they have color charge, so you exclude the quarks, gluons, the double-D bosons, the charged leptons. So neutral particles, it is the neutrinos, photons, C boson, and Higgs boson. Stable is only the neutrinos and the photon, but of course the neutrinos are radiation, they are relativistic at the time of transformation, and they are not the it's not the candidate of that. So it's this very well known fact that the existence of this non-luminous component of matter in our universe constitutes an evidence for physics beyond estimation. So this is something that has been addressed at length in the last 30, 40 years. So there are many particles that have been proposed. So this is just a sample of these particles in planetary space of the cross-section with nuclei against the mass. So this planetary space is populated by many candidates, many more which are not in this figure. But maybe what is notable about this figure is the diversity of candidates that you have. You have candidates with masses between the microelectron volt or very lighter particles that have masses up to the grand inflection scale into the 15 GeV. And then for the cross sections, for the strength of interactions with the nuclei, you have particles that are very good interacting and detectable in practice, and then particles that have sizable interactions. And also, maybe one of the big puzzles of the dark matter is why there is dark matter today in the universe. So you have to have a particle which is sufficiently long-lived, must have a lifetime which is longer than the age of the universe. And you know that in the standard model there are very few particles that which with this characteristic. It is only the proton, which is stable due to the environmental conservation. The electron, which is stable because it's the lightest particle that has electric charge by the neutrinos, because they are the lightest spin of half fermions, and those are the only particles that are expected to be absolutely stable. And then once you give up on these symmetries by the number, electric charge, Lorentz invariance, then the next particle you have in longevity is the neutron. So here it is a bit long-lived because of the approximate isospin symmetry, but in this case the neutron has a lifetime of 13 minutes, which is far away from being cosmically stable. So as long as you have an exact symmetry or any other reason to have this matter stable, then this matter will typically decay very fast. And yes, it is the problem with most of these candidates for large masses that in order to establish that decay, you have to impose a symmetry. Could be a C2 symmetry, could be a pi conservation, integration supersymmetry, etc. You have to impose some new elements in your theory, in your model, and on the other hand, you have these light candidates where the longevity of matter is due to the smallness of the matter candidate, or due to the small phase space which is available for this particle today. But this is another puzzle why dark matter is so stable, so that it is existing, pillars and us today in our universe. So the question is whether it is a new symmetry, it is something about the phase space for the decay, it is something that symmetry, or why it is so stable. So it's something that at the moment we don't. Okay, so the last or the third element in this energy tensor is the cosmic constant. So here we are not even close to explain this in the context of the standard model. So there is no known particle or no known field that generates a fluid that has negative pressure. So it is one of the biggest puzzles in fundamental physics. So I'm not going to enter into that either. And then the last element of this from this neutron tensor is the luminous matter. And then here we have some interesting candidates for the luminous matter in the universe, because we have here these fermions of the first generation that have color charge and that have aromatic charge, and that eventually give us candidates for cosmically stable luminous matter, which is the proton, at the state of quarks and quarks, the electrons, and then the neutrons. As you know, they are not stable when they are free particles, but they're stable when they're bound to protons and to the nucleus in the nucleus. So we have also good candidates in standard model for the luminous matter, but that is not the story, because we don't know what is the luminous antimatter. So as you know, quantum field theory makes no difference between particles and particles. And then the question is, why do we have these particles, many particles of this in the universe? We have many protons, many electrons, and we have so few antiprotons, and so few positrons, and so few anti-neutrons. And yeah, so it has been quantified since many, many years. It's typically measured with this quantity, number of baryons minus number of antibaryons divided by the entropy density. And this quantity today has this value. So it is about 10 to the minus 10. So this means that the number of baryons divided by the entropy density today is about 10 to the minus 10. And yeah, so this question was already addressed in the early days of particle physics or cosmology by Alejandro in 1967. And then his question was whether it was possible to generate a universe with this asymmetry between baryons and antibaryons, given the fact that the equations in quantum field theory are symmetric and the exchange of particles and antiparticles. So what he showed in 1967 is that it is possible to start with a universe which is baryon symmetric, but you could generate this asymmetry if you have a theory that varies by a number, you have C and C evaluation, and you have a departure from thermal equilibrium. This is the known mechanism of baryogenesis that has been the guiding principle for model building and for cosmology over the last 40 years. And remarkably, all these conditions exist in standard models. So you have variation by the number via invertible processes via spirals. You have C and C evaluation in the weak sector, the CKL matrix, and also you have the departure from the equilibrium via the expansion of the universe. However, it has been shown already a long time ago that both the C and the evaluation is not enough to produce the observed difference between number of baryons and number of antibaryons over the entropy density, and the same with the departure from the equilibrium, because the phase transition is not of the first order, and also because typically this violation of number is not. So again, here the existence of this number, or the existence of more particles and the part of the universe, is an evidence for physics beyond this number. So this has been discussed, as I say, at length. So there are many extensions of the standard model that fulfill the three Sakharov conditions, and that can generate the baryon symmetry as indicated, or this G, as indicated by observations of the CMB and the cosmic macro and the Big Bang synthesis. So this is a complete list. For example, we have baryogenesis. It's this standard mechanism of baryogenesis that we have here, but extended with extra singlets or extra doublets, so that you have more sources of evaluation, so that you have first order phase transition, etc. A second framework, very popular, also here in this group, is the leptogenesis via the decay of the heavy right-handed neutrinos, in the 80s. So more recently, there was a proposal by Rudolph and Smirnov to have neutrino oscillations, these two sterile and then these ones with the protein leptogenesis, and eventually baryogenesis via the phase transition. Also in the context of the stimulator, you would have reflectile baryogenesis of leptogenesis plus many. So this is something that has been very well studied, and actually there are many mechanisms, quite successful, all of them, some of them more testable than others, but all these mechanisms can in principle accommodate this. However, this is a series of models that were cooked up or they were devised thinking mostly of the boundary symmetry of the universe, but these models are typically connected to other constant cosmology, in particular diagonal. These models, there is typically no connection to them. Okay, so this is well known, all of this, so now I'm going to tell you about our recent ideas. Some of them are provocative, and of course I'm open to discuss with you these ideas. And just in general, when you are stuck in a problem, then either you can make your model more complicated, you can make new models, or you can start thinking about what is why you stuck. And then, I would like to think of this fact that it was the cosmic pie at the time of Sakharov, 1967. So remember that the cosmic macrowave background radiation had been discovered in 1964. So this means that it was known that the universe was very, very hot in the past. In the past, the universe was radiation dominated. That today the universe was matter dominated, but not more than that was known. So, particularly at that time, it was not known whether the universe or the three-dimensional space-like hypersurfaces, whether they were especially flat, when they were open or they were closed. So it was not known the omega curvature, if you want. Also, since you don't know what is the total omega of the universe, you know what is the total curvature, then you know what is the contribution to the omega from the baryons, etc., and the nucleons. So many things in cosmology were happening. But today we have a much better determination of the cosmic pie, so we know that the total omega is equal to 1. So it means the universe is especially flat. We know that ordinary matter amounts for 5% of the universe, dark matter 27%, dark energy the remaining 69%. And so with this new picture that we have of the cosmic pie in this decade, then we cannot say that there is an evidence for the boundary symmetry in the universe. So even in contradiction with some statements in literature, but here the one that I want to make is that many of the statements that we have in the literature about boundary symmetry in the universe is based in this cosmic pie. It's not based on this cosmic pie. Because what we know for sure is that in this sector we have more baryons than antibaryons, but we cannot say that there are more baryons than antibaryons in the whole universe. So it could happen that here in this dark sector, especially in this dark sector, we have particles that have baryon number, and then with this information we cannot say that there is a baryon asymmetry in the universe. What we can say is that there is a baryon asymmetry in individual sectors, but it could even happen that the universe is bound symmetry, and that part of the asymmetry is compensated with an asymmetry in the dark sector.
So what you mean is in the ordinary matter sector, they are bound asymmetry, and dark matter sector, they are also bound asymmetry, but in total they are symmetry.
Yeah. So it's like a game changer. It's like a game changer. Because, the difference is clear, no? In the times of Sakharov, the whole universe was visible universe. So, since you were seeing more protons than antiprotons, then you can see that the universe is bound symmetry. But now we also have the dark sector. We don't know what is the baryon number of the particles in the dark sector. Baryon number is simply global symmetry, and perhaps these particles in the dark sector are charged and distributed symmetry. And what we can see already for sure is that you have more holes than antiquarks. But with more particles carry a baryon number apart from the bond. And then if you accept this fact, then it could even happen that our conditions are not necessary. Typically, it's the statement that our conditions are necessary to explain the universe as we see it. But again, this is thinking that all the baryons are in the zero sector. If some baryons are in the dark sector, perhaps you have to reconsider what is happening. And so this text is just a bit. And then we came up with a mathematical recipe to cook the cosmic pie, which is not using the same conditions. So here you see that there is no, in principle, no necessity for binary evaluation. And then instead what we need is to have that set of particles with our number. And then what I'm going to show with one example in 3 minutes is that one can generate a quark and a quark asymmetry, and one can also generate a cosmic pi, that is for the matter sector as the one that you observe, if you have C and C violation in that sector, because we want to generate an asymmetry between particles and the particles in that sector carry by a number. And this is easier to do than in the visible sector, because for the electrodynamics, for example, we have constraints on the masses. But for example, in that sector, since we don't know anything, it is quite easy to generate anything that you want. And I'm going to show that later. Yeah, so to generate an asymmetry between particles carried by numbers and the particles, then you have to impose or to accept or to postulate some important interactions between that sector and the visible sector. So this asymmetry that you need in that sector is linked to the visible sector. And then finally you have to require the partial functional equilibrium in the standard framework to prevent the push out of the asymmetry. And yes, it is a simple scenario that fulfills these alternative conditions. Of course, it's not as I'm saying as a conditional problem, it's just an alternative recipe. So a simple scenario, so of course, we're going to take some other quarks. I have a number equal to 1/3. To make this framework maybe more spectacular or more notable, I'm going to impose binary conservation. So here I'm explicitly violating the first sample condition. Okay. But this is what saves the day. So I'm going to introduce a complex scalar that has binomial equal to -1, let's call it chi. And I'm going to introduce the Dirac fermion that has binomial number equal to +1. And with these three particle contents, then you can automatically generate the quark and the quark asymmetry if you have a mechanism that generates more n than anti-n. And this can be done, for example, from the out of equality of the heavy particle. So, to give you an example, you have to have important interactions between that sector and the visual sector. And here you see that with these global numbers, you can have these neutral important interactions with the doubling between this particle n, which is singlet, and the standard model is 2, and then this combination of quarks, this one is the equality neutron portal. And this because this is the neutron, U, and this is a particle that is also neutral, and this is, as I'm going to discuss later, is a kind of interactions that eventually will produce a mixing between the neutron and what is sometimes called the mirror neutron, which is this thing. And finally, I'm going to require a partial fundamental equilibrium in the standard. Okay, so why am I so excited about this thing? Well, first of all, because here I want to show
scalar and fermion, chi and n belong to that sector.
Yes, yes. So these particles are singlets, and it's another H2.
In the standard model H2.
Yeah. And they have this transformation under the bound number global group. Okay, so when I'm discussing this quark and the quark asymmetry, because I have n and bar, but here I don't have chi. So what is chi doing for me? And why am I introducing this field chi? Well, the first thing is because chi also has a value number, so I have to introduce it to ensure the conservation of the value number of the universe, so the case of the universe. And this, for example, can be done via something like electrodynamics. For example, you can introduce here a particle, phi, that has value number equal to 0. It decays into one particle that has value number equal to 1, value number equal to -1. And then when you take these couplings to be complex, like electrogenesis, here you shall have more than 1, then the interference between these decays plus the loops will generate an asymmetry in n, and then the corresponding asymmetry in chi. But since this decay is a power number, the total power number is going to be equal to 0. But I'm going to generate here an asymmetry in n and the corresponding asymmetry in chi. Right? So similar to what we were discussing this morning. So like this, with this chi, I can ensure that the boundary number is equal to 0 in the whole critical history. And moreover, chi is a scalar particle. Chi carries boundary number, and then chi cannot decay. Chi cannot decay. Simply because the boundary number is supposed to be constant. You can just think, but there is no possible way to make chi decay in a way that preserves the boundary number.
So why can't it decay into a, for example, neutron?
Yeah.
An anti-neutron?
Because you have to preserve the boundary number, the Lorentz symmetry. Chi is a scalar, the unit is a fermion.
Okay. So you mean the car is the lightest scalar?
No, it's not the lightest. It's not the lightest scalar. Well, okay, it is the lightest scalar that's boundary number.
Yeah, that takes the boundary number.
Exactly. So it makes it stable. So it is why I find it so exciting, because in this framework, which is practically simple, then if you have organ level symmetry, automatically you have a dark matter.
Why is scalar has file number? Is there any unique condition?
It's a complex scalar. It's a complex scalar,
Oh,
so it has a boundary number.
oh, one charge.
It's a U-bar charge.
So the symmetry is also rising the dark sector M and transfer it to the luminous particle by the neutrino portal.
Exactly. Okay, I'll go into these details in a second. That is a general picture. I will go to details, in particular, say a good one. So this general picture, I say here, the interesting part is that you have this connection between organ level symmetry and the existence of dark matter. And also that the dark matter is stable not because it imposes into symmetry, not because it imposes a binary conservation. Dark matter is stable because of the binary conservation. So you have to impose the symmetry. It is there on the conservation. Okay, so now let's go into details. So this is our initial state. So here, this is the populations of particles and the particles in the dark sector, the population of quarks and quarks in the visible sector. So you see that here, initially, we have more chi's than chi stars. We have correspondingly more n's than n bars. So here, in yellow, you have the particles that have boundary number equal to -1, or negative boundary number. And then in blue you have the particles that have positive boundary number. So the total area of the yellow part and the blue part are exactly the same. So you have equal number of baryons than anti-baryons. And then in the initial state for the visual sector, you have equal number of quarks and anti-quarks. Now here you have different portals. You have different interactions between the particle in the dark sector, chi star and n bar n. This is allowed by the symmetries, by the amplitude. So in particular, this is the current, which is mediated by a particle with spin with pi number equal to 0. This one is mediated by a current that has pi number equal to 2. And then, as we were asking before, here you have the electron portal. This is what connects the dark sector to the visual sector. And it is very important because there is no way to connect these scalars with the quarks, at least at dimension 5 and dimension 6, in a way that is preserving the boundary number. So now you leave your system evolve. So here you will have the leakage of this asymmetry from n's into the quarks. Eventually, you will end up with an excess of quarks and anti-quarks, which is what you observe in experiments. And since the boundary number has to be preserved, you must have the remaining boundary number somewhere in that sector. So you see that we have been able to produce the boundary symmetry of the universe with boundary number conservation, so without the first self-condition, and the prediction of this framework is that we have that. This is what you were asking before. But now the remaining boundary number is stored in the dark sector. So things are a bit more difficult in practice because typically these processes happen at high energies. So this means that the spirals are in thermal equilibrium. So here you have one important between the core sector and the electron sector. But nevertheless, the picture remains the same. So yeah, for simplicity, I want to assume, just to make it more refined, more concrete, I want to assume that these two sectors have the same temperature. Because typically, you could have different temperatures. But if they are thermalized, then I only have to worry about one parameter, which is the temperature of the universe, the temperature of the sector, temperature of the dark sector, temperature of the universe. And I want to suppress these scatterings that would wash out the asymmetry, so I want to impose that this portal is very simple. That's for simplicity. So then we are left with these two portals. Plus the portal of this with the spirals, which is known. And then let's see what would happen with this thing. You can imagine what is going to be the story is that we're going to have an excess of quarks over networks, an excess of anti-electrons for electrons, and then the rest is going to be in this chi sector, this diagonal sector. Okay, so here this is the evolution of the different asymmetries and different yields with the temperature. This is kind of solving the Boltzmann equations. I'm not going to write down the Boltzmann equations, there are many, not very important, but these are the main conclusions. So here we start initially with the yield for n equal to 2 times the yield of chi, simply because you have a double number degrees of freedom. You have equal asymmetries for n's and chi's. That is because of this reduced scenario, and also because you want to ensure that the one is equal to 0 in the universe at all times. And also that initially you have no asymmetry between quarks and quarks, or any asymmetry between leptons and electrons. So the first thing that you realize is that as soon as you put this system into evolution, then you have an asymmetry generated in the quark sector and the electron sector. The asymmetry in the quark sector is generated via this scattering, so they have an asymmetry between n and anti-n, and these processes would lead electron asymmetry between quarks and anti-quarks. And then part of the asymmetry is transferred to electron sector via the spiral. So at the end you get these predictions for the asymmetries at this stage, for the delta L, for the delta chi, for the quarks and for the leptons, and all these parameters are calculable via the chemical equilibration of the different particle species. So this is something which is easily calculable. Now there is a second stage of transmission of the asymmetry from the dark sector to the visible sector, which is clearly the case of this fermion n into quarks. And this one further increases the quark and the quark asymmetry. So this is the one that we had before. And now in this case, generate this as a totally which have the quarks. And this is the final asymmetry that you obtain in terms of initial asymmetry. And again, these factors are calculable just from the chemical equilibration of the spirals with the standard model, and for the chemical equilibration of the different particle species. And yes, since typically this decays happen quite late, then the electron asymmetry is frozen, and this is why it is not changing compared to the values that you had when the spirals were in thermal equilibrium. And these are just details, but just to show you that one can make calculations in this framework. And yes, so this is about the evolution of the yields over the asymmetries. What about the evolution of the total yields? That is, here is dashed lines. So here you have the yield of the dark matter of chi, this is scalar, and eventually you have the freeze out of the operation of dark matter particles of the high temperatures. You have annihilations into n and anti-n, and investigations and so on, and then eventually these processes freeze out, and then you can calculate with this periodic abundance of this dark matter particle today in terms of the mass of dark matter and the temperature at which this process freezes out. This is standard, this is like contour mean, and this is pretty well established. So basically, the bottom line is that the asymmetries, today the quarks is related to the asymmetries initially in the dark matter sector, and the omegas, the periodic abundance of dark matter today, is related to the yield of dark matter particles on the freeze out and the mass of the dark matter. This is a summary that you have the possible final states. The first final state is when all the chi stars are annihilated, so this is the picture that we had before, basically. Forget about this part with the vectors, because it's basically what we had before, in a bit more complicated because of the sudden transitions. And yeah, so what you see is that you have quark and quark asymmetry, you have electron and electron asymmetry, you have dark matter, and the balance of dark matter is predicted in terms of the heat of dark matter frees out, and the mass of dark matter, and the heat of dark matter, since you have a dark matter, is equal to the asymmetry, which is related to this asymmetry in the dark matter state. So anyways, these are just technical details, but just to say that one can make this correlation between the abundance of the matter particles and the abundance of quarks. And then since we have here these two different parameters, then at the end you can predict that the dark matter is going to be about 3.4 G in this framework. And in order to explain the one asymmetry, or the quark and the one asymmetry, you have to postulate that this asymmetry between particle and the particle in the sector must be about 10 to the And then this is that this is something which is relatively easy to produce, because remember this is the mechanism that we have to relate the asymmetry between chi and anti-chi, or between n and anti-n, and the mass of these particles are free parameters. These two couples are free parameters, the phase are free parameters, and also the mass of these final particles, and this is not correlated at all with anything that we see in experiments important. So here you have plenty of opportunities to explain the asymmetry of temporal state, and as you know very well, it's a typical number for asymmetries that one gets in experiments. So typically one has to postulate that you have these particles that have masses 10 to the 9, 10 to the 10, 10 to the 7, 10 to the 11 GeV. You have here couplings that can be for the 1, to the minus 2, doesn't matter, but you have the large particle space where you can produce the asymmetry that you require to explain. And yeah, so I insist that with this data, you can produce a quark and a quark asymmetry which is 10 to the minus 10, as we see in experiments, and you can produce the dark matter abundance today, which is equal to 0.12 material particles. So this alternative scenario, when not all chi, but there is also some fragment of chi star, when the annihilation is not complete. And then the discussion is basically the same, but in this case, we obtain an upper limit on the mass of the matter particles, which is about 3.4. Typically, we expect in this kind of frameworks the dark matter mass, which is 3.4 GeV per particle. Yeah, so this is like an interesting, well, we find that this is an interesting scenario, because it allows first of all to say comparing the static conditions that were believed to be necessary. They are not necessary once you accept that there could be particles in that sector that have the number. This idea is something which is not just like an intellectual exercise, but also gives you something, gives you that matter automatically. And what I want to discuss in the last maybe 10-15 minutes is what are the possible experimental tests of this idea. So the experimental tests, they have to come via the portals in the mathematical model. In this framework, we have two portals. The Higgs portal that I have not discussed, also because this portal basically has no impact in the evolution of the particle species. This does not change the volume of the initial particles. And yeah, so this portal could be tested, for example, using the Higgs visible decay width. So the Higgs could decay into two matter particles, and this has been searched for by the Atlas and the Siemens experiments. And using the fact that there is upper limit on the vacuum fraction of this invisible, then this allows to put this upper limit on this vortex coupling, which is about 10 to the minus 2. Also, there are limits from direct detection experiments, so if you want, there is an opportunity to detect these matter candidates from direct detection experiments. So here, the first thing to know is that these frameworks predict a matter mass of about 3.4 GeV. So it's typically much smaller than the range of most dark matter detection experiments, like Chino or LZ or Panda X. They have typically like a threshold. But there have been different ideas in recent years of how to extend the range of experiments to lower dark matter masses. So this is the limit that was released by the large site experiment in 2022. Compared to these smaller experiments, here must be zero experiment that I can see here. And you see that now experiments are really getting close, or closing in this region of light dark matter, in particular, the light dark matter thing is for us, which is a mass of 3.4 GeV of the hybrid internet. So again, the non-detection of a signal in the detection experiments tells us that this quartic coupling cannot be bigger than 10 to minus 2, as is with standard assumptions about the strings. Also, if the matter is partially asymmetric, you have a position of chi and chi star, you will have signals in infrared detection experiments. In the simplest framework, the matter is totally asymmetric, so there is no annihilations in our galaxy today. And then, as a note, there is a theoretical limit on this quartic coupling that comes from the fact that when the Higgs gets an explanation value, then this amounts to a contribution to the dark matter mass. So if we want to give the dark matter mass at 3.4 GeV, and given that the Higgs spec is 170 GeV, then we have to impose there is no quartic coupling. So to give the mass at the 3 GeV, then we have to impose that this quartic coupling must be smaller than 2 times 10 times. So if you take seriously this naturalist constraint, then it's going to be quite difficult to see signals of the model, either in the Higgs invisibility theory or in the detection experiments. Also, there could be cancellations, there could be some other mechanisms that produce these cancellations. And so what I want to say is that I don't think that's going to be the best way to test this scenario, but one has to be parallel. One has to complement the experiments and say for that matter, this mass is between 1 GeV and 10 GeV. Okay, more important or more interesting is the neutron portal. So here, the neutron portal is described in this way. So it's dimension 6 operator, surfaced by 2 powers of the energy scale. So here the boundary space is spanned by this strength of this dimension 6 operator, and then the mass of this fermion n. So remember that the mass of the matter particle is fixed, 3.4 GeV, but the mass of this Dirac fermion is not fixed. So one has to try to constrain these boundaries. And one possible way to constrain the boundary space is via proton decay. Okay. What you were saying before. At least it's different because time cannot decay because it's a scalar, but now here these particles are fermions. So now here these ones are important in this case. So if n is very light, then in principle here this interaction with the proton could decay into this n that is now the lightest fermion environment, and the pion. This has been observed, of course, by Spencer and Campbell, and then when you have very, very light masses for this n, then this is really light. Also, this induces a decay of n into hadrons. So this is typically quite bad for big nucleosynthesis. If this decay happens very late. So if this neutron portal is very, very large, then typically these particles decay during or after big nucleosynthesis, and then you could exploit against predictions of the standard BBN signal. So in order to avoid problems with the BBN, then one can impose that the lifetime of n is smaller than 0.1 second. So this means that this strength of this dimension operator cannot be too much. So that this particle decays relatively fast. Also, we have constraints coming from the LHC. So again, this portal interaction uses partonic cross sections of 2 quarks to produce one of these mirror neutrons and one anti-quark. And then one can estimate what is the cross section for these processes. So this is the number in terms of the strength of this interaction. And yeah, so this is the typical contours of the cross section production. And this is the typical quarter rate, which is about 300 femtobarns. So everything which is below is probably ruled out because the would have produced it already. And everything which is above is safe because the production cross section is too small to produce this end as invisible energy jets at the edge. So of course, when you go to these small mediators, then one has to be careful about the validity of the relativity theory. And that is one of the things that we're doing now. We're trying to find the new completions of these portals, and for the other portals of the theory, and then to see whether this mediator that induces portal can be detected at energy or not, or whether this mediator can have an implication in the cosmology. And then finally, another thing, that here I can assume for simplicity that we have the neutron portal, so that this particle couples into the first tension of fermions, but you would have more complicated or different portals. You would have what we call the charm omega portal, where this mirror neutron, or this mirror particle, this black helium particle, couples not to the first generation of quarks, but couples to the second generation of quarks. So in this case, still the cosmology works exactly the same, because everything happens at very high temperatures, so there's no difference between the strange quark and charm quark. But in the protons, you don't have so much strange and charm quarks. So then, of course, when you have this charm omega portal, the production cross sections at energy are going to be much more dense. So in this case, if it is the correct scenario, then some of this planetary space would open. And then finally, there is this other constraint at very high energies, high masses. And that is because here, in this simple scenario, we have been assuming that we have this inner particle content, and then chi can only annihilate into n at n. So clearly these annihilations can only happen if n is sufficiently light. So typically, you would say that can only happen if n is lighter than chi. So you could give us a limit on mass of n, which is about 3.4 GeV. But you see that we don't have some planetary space open here, because there are some particles in the thermal path of this species of chi that have very high velocities. They are lying at the tail of the mass of distribution, and then they are sufficiently energetic to produce n and n, even if the mass is above 3.4 GeV. This one is called the Fourier channels that have been analyzed already some years ago by Lewis and Second, which famous the three exceptions for the calculation of the harmonics. And yeah, so here the bottom line is that we have a parameter space, which is bounded from above, from below, from the left, from the right, and which in principle testable. But of course, some of the parameter space could open, particularly here on the right hand side, if that matter annihilates into other tangential photons or into like scalars, etc. Then we will have this constraint on the dark matter of the mass of n for high masses. So this is the version that we have already published. To tell you some work which is now in progress, which is to analyze the electronic version of this framework. So the idea is exactly the same. The idea is to have a dark sector where one has this black fermion, and we will have this scalar, that you have this portal between n and the visible sector, and this standard Yukawa coupling, so n could be a neutrino. And here the idea is exactly the same. The idea is that eventually this asymmetry we have between n and n will lead to the visible sectors to have an asymmetry anti-L and L, and ultimately an asymmetry in the pores via the spirals. And then the remaining electron asymmetry will be stored here in that sector, and this protocol will be absolutely stable because of the electron number conservation. So it's exactly the same idea, but not here using the electrons. Now here the advantage is that here you have portal interactions which are normalizable, and portal interactions that could give implications for multi-masses. So one of the things that we are interested in happening. Okay, so this is basically everything I wanted to say. So maybe one of the hopefully interesting conclusions for you, something which is maybe obvious but maybe not so much stress, so perhaps even unknown, is that there is no evidence for eventually. It's something that is obvious in hindsight, but it's something that people would not notice before. Observations only show that the more Poisson works, but the wave particles in the dark sector also carry variable number, and then, as I showed today, that could be a quark at the quark asymmetry without fulfilling some conditions. So some conditions are a possibility, but are not the only possibility to generate a universe that the one that is. So now this possibility has traditional the interest that you have dark matter which is stable due to the dynamic conservation. You have to impose a new state. This theory is also predictive because it tells you that the mass of this matter particle must be 3.4 GeV, and furthermore this scenario is in principle testable because you have signals at color experiments, in photosynthesis, but also in theophysics. If you want, we can discuss about the signals in theophysics. So thank you for your attention.
We usually said the dark matter is non-bionic. So does it contradict with
No, exactly. That is one of the sources of confusion because that is the terminology from the astronomers. So normally is for astronomers, but for astronomers the baryon is a particle that couples to the photon in a similar way as the proton. So when astronomer means that the dark matter cannot have power number, this means that the matter particle cannot have couplings to the photon which are sizable and cannot have some interactions which are sizable. But it's not about the global number, it's simply about the properties, that the properties are similar to the properties of the known values. Like this number that have been used for many years, and that I think was a very confusing terminology.
I have a question about, I think some kind of model connecting the dark matter stability with the baryon number symmetry. Maybe it's not a new idea.
It's not a new idea.
Okay.
Yeah.
And I think when I started to investigate the symmetric dark matter, I saw some authors connect these two things together.
No, but that's different. It is different. It's different because most of the models of estimated dark matter, what they do is that they introduce a dark matter number. They introduce an extra G1 symmetry,
Yeah.
and then they use Sagan conditions in order to produce an asymmetry between particle and the particle, and you have a portal to visual sector. So this one is even more minimal in the sense that you have to impose even this extra G1 symmetry. So it is just the baryon symmetry. So that's it.
So because you utilize the baryon number symmetry U1 other than the additional U1 symmetry, so you believe that you are not an asymmetric dark matter?
It is asymmetric. It's asymmetric, but you have to have new ingredients. So this one is for minimal. And also because models of dark matter, the models of asymmetric dark matter typically you only put one particle in the dark sector.
One particle?
In the dark sector. Yeah, and then what they do is that they generate an asymmetry in this particle in the U1 dark, and then the U1 dark is connected to the U1 baryonic via spirals, and they produce an asymmetry in the baryons.
You mean that they still have additional U1?
They have additional U1. But the interest of this, of the new element, is that you put another particle in that sector, then you can have the baryon number conserved in the whole evolution. But in those models of asymmetric dark matter, you still have to have the variation of baryon number, and you have to have the variation of this U1 or U1 dark, because you want to have Sagan conditions. So at the end, they learn on the Sagan conditions.
Another question is that have you ever considered about the UV completion version of your?
Yes.
Okay.
Yes. Yes. It is now work in progress. And so, for example, here we have several portals. Yeah. We have this one that we don't want. Yeah. And this portal is actually generated by this interaction. But this is good because we want to have the definition of the symmetry in the case of these heavy particles. And then, since particles are heavy, then naturally this portal is going to be suppressed. Now for this one, we have to have, again, we don't need it, because we want to have a portal for this neutron proton interaction that is via a scalar.
Yeah, but you might have to introduce some squawks.
Yes, these squares are here. These squares are here.
Yeah, I mean you might have to introduce some S-quarks,
It's like scalar
the
quarks.
scalar quarks.
Yes, you have to introduce some scalar particles that have color. And
So it's work in progress.
so it is progress, yes. But that is fine because you see that for us, for this mechanism to work, then you have to have these scalar quarks with mass of 10 to the 4, 10 to the 5 GeV, so we are safe. And what is also interesting is that these scalar quarks, via loops, they produce an interaction which is chi star gluon gluon. And this is good for the freeze out. So you don't have to have any portal for this. This portal, or the portal of chi into gluon gluon, the portal which is important for the freeze out, this one. This freeze out will happen via chi into glue at the one loop level via these quarks. So the UV completion turns out to be even simpler than the effective theory description. And also has an interesting phenomenology because of the polarized signals. You have produced directly these new particles, you have represented channels, and also here you have implications of flavor physics. What is that? Yeah, exactly here. So for example, from here you would have a baryon decaying to N and the meson. Okay. So at least a channel that perhaps, for the delta of course, but for example with the delta. Yeah, no, the delta resonance. The delta resonance would decay into a baryon and the invisible energy. So in principle, there is something that could have been interpreted as a baryon number baryon channel, because you start with a baryon and you see a meson. But here in this context, this baryon number is being carried away by the invisible energy. So it's a channel that preserves baryon number, but it's very peculiar because it is baryon into a meson and invisible. So there's necessity for that, and now we are in discussion with some people from there to make this analysis more. So it has an interesting framework also.
In the section, the simple scalar will, the complex scalar will the baryon number -1 in the follow page.
In there?
In the follow page, in the session, the simple here.
So which one before or after?
Maybe follow page.
Let's have a quick stop.
-1. Oh yeah, this. What the meaning -1 and +1? What conclusion we can get in these two ways?
Yeah, it is -1 and +1 because of this. I mean, it's just a question of the notation. With chi has -1,
Oh.
n plus as 1, but here the idea is that you have the total blue areas must be equal to the area because you want to preserve the Raman number. But if you don't think this is the case, you have phi into chi and n. So chi is -1, n is +1, but you have the phi into chi star and n, for example, no? Depends on how you define these things.
I have another question about the calculation of the. You have computed the decay rate of the n, n into proton plus pi plus or into neutron plus pi 0, and I'm looking into your paper and found that there's no citation about this calculation. So, because this involves some non-perturbative techniques, so how did you do that?
Yeah, because here it's not so important.
Yeah,
I mean, for you it's important, but for us it's not so important because you see that it is excluded as soon as it is open. Okay?
What?
That you see that here this planetary space goes up to the 5 and to the 6.
Okay.
So the thing is that maybe with your calculation, you would say that precisely that lambda has been is more than 10 to the 16 GeV.
Okay.
But for us, it is not important if it is 10 to the 16 or 15.7 or
Yeah.
because at the end in this planetary space, for sure, everything here should down. You are right that if you continue extending this up to 10 to the 16 GeV, at some point you will have here a term. Because maybe it becomes allowed.
Maybe there is a little bit difference between your paper and the PPT you have and the slide you have shown. And in your paper, you just calculate the decay rate of the n, but here you calculate the decay rate of the proton.
Okay. Because here this is for the proton, but now here we have the decay rate of the n. This one.
I mean, how did you acquire this?
Yeah. Well, first of all, we have this. But also here, you see that this is before the confinement. I mean, here we're very careful. Actually, I said this question I had with my collaborators because initially we put these constraints to be 1 second.
Okay.
So 1 second corresponds to 100 MeV, which is precisely when you have to start the confinement. But at 0.1 second, the temperature is 1 GeV. So you can still talk about the free quartz.
You got it. All this UDD as free quartz.
Yeah, exactly. But that is because here, when imposing that the decay rate, the decay rate must be smaller than 0.1 second. And here, at this temperature, you can still talk about the free quartz. So now you are right that if you have put the limit at 1 second, like maybe more aggressive, more conservative, I don't know, this is very conservative. If you put the limit at 1 second, then you have to care about the harmonization. But if you put this limit, here you can still consider free quartz. It's just an approximate. It's an approximate value. But now, as you say, perhaps this point here, or perhaps this point here, I mean, for sure, everything here is around.
So if these are calculated below maybe 100 mega EV after the confinement, so we have to use some non-perturbative.
Yes, exactly. But at these temperatures, at this impulses requirement, then you don't have to worry about this. You have to worry about this when you really go to the epoch of period. And for sure, then you have the products and but this is just very conservative, and also because this is very rough. It's a log scale, but you are right. I mean, we're aware of all these limitations, but just here the whole point of this plot was to show that the planetary space is bounded from all directions. But certainly here there is room to make things more carefully. I'm interested about your paper. You have to tell me which is the reference.
What?
You have to tell me what the reference of your paper. Because you said that you have looked at that carefully, no? You said that you have looked at this decay.
No. I'm just looking into your paper.
Okay. No, but you said that you have calculated that.
No. I didn't mean that because
Okay.
I'm just looking into your paper and find.
Yeah.
And maybe I got some misunderstanding about this N2 UDD. I thought you were talking about the N2 neutron.
Yeah, exactly, because strictly actually we have some calculations to have n into neutron gamma, for example, with the hadrons. But at this temperatures, or at this energy, so at this regime of lifetime, 0.1 second, that is not the one that you see.
Yeah.
You can consider all this as free.
Maybe I got some misunderstanding about this one.
Yeah. But thanks for the comment.
Okay. Any more questions? 有没有问题？ Okay, let's thank speaker again.